Okay, so this is a follow-up to my other video where we used the washer method for a vertical axis of rotation. Okay, we rotated x squared plus 1 around the y-axis. So this is going to be the same function, y equals x squared plus 1, but we're going to change the bounds a little bit, and we're going to go into this is an example where you have to kind of use two different integrals and then add them together. So we'll see what I'm saying. Okay, so let's let R be the region in the first quadrant bounded by y equals x squared plus 1. Okay, so same curve there. X equals 1. It's also the same. But now we're going to go all the way down to the x-axis. All right. Now we're going to rotate R around the y-axis just like last time. Okay. So let's make a sketch of our drawing. Or sorry, a sketch of our region. Okay, so let's see. We have y equals x squared plus 1. So that's a parabola that intersects the y-axis at 1. So this point here is 0, 1. Okay, now we're also going to take the vertical line x equals 1. It's right here. I should label that y equals x squared plus 1. Okay, and now the other, it's bounded in the first quadrant. So it's just this and the x-axis. So first quadrant, it's just this area in the first quadrant. And it's bounded by the x-axis, x equals 1, and x squared plus 1. So it's all this in here. So it's a little different than the last video. This just going a little bit further down. Alright, but that actually changes things in a lot of ways. Okay, now we're still going to rotate around the y-axis. Now our shape is something like this. Goes all the way down. This, down. And now rotate it around the y-axis. Okay, so again we have the bowl happening. But under the bowl, the solid is kind of extended all the way to the x-axis. Okay. So again, it's kind of like a cylinder on the outside and then a bowl on the inside. Now we have to do this in two different pieces actually, and you'll see why. Alright, so remember this point here is 1, 2. So that's a point where x equals 1, and then you can substitute into x squared plus 1, 1 squared plus 1, that's 2. So that's the point where x equals 1 hits the curve y equals x squared plus 1. Okay, but we have to actually break this up into two different integrals, and that's because if we want to use, we see that we need a washer method integral. Let's see, we need a washer method integral right here because, right, we have some piece missing. And here would be the small radius. And from here to here would be the large radius. But down at the bottom, let's see, down at the bottom here, I don't have that. I just have one radius. So that bottom half has a different radius. Well, it has the same radius as, same outside radius, but it doesn't have an inside radius. It doesn't have a small radius. Those are both the same there. So, we're actually going to combine a washer method integral and a disk method integral. Pretty exciting. Okay, so let's see where those split in half. Okay, and it splits in half, as you can see, is right here. So where it splits between the bottom half and the top half is at 1. It's halfway through. Halfway through the height. So this would be 1, 1, that point there at the end. Okay. So now, if you recall from last time, little r of y, that's going to be given by y minus 1. Big R of y, that's going to be given by just 1. And now we're going to have a second r of y, a second large radius, and that's also given by 1 for this bottom part. So it's kind of like we're splitting this into two pieces. So we're going to do this piece first. And then this piece next. And if we want to find the volume of both, no, that doesn't. That should look even. If we want to find the volume of the total solid, we need to just add them together. Okay, so let's see. Let's do the top first, because the top we already did in a different video. And if you have questions on where I got little r of y and cap r of y for that, you can go back to that video. Okay, so our volume is going to be pi times the integral from 1 to 2 of big R of y squared minus little r of y squared dy. Okay, so just clean that up. Alright, so that's the volume of the top piece. We'll call this the top piece. Alright, now we need to add the integral of the bottom piece. Now the bottom piece, the bounds are going to be 0 to 1 because that's the vertical range of that bottom piece. We saw here, between 0 and 1. Okay, and this is going to be a disk method integral because there's no space missing. There's no it's completely solid, and it's really just a cylinder. You could actually use the volume of a cylinder of height 1 and radius 1 if you wanted to. But let's keep it with the integration, and we'll have a disk integration, and again that outside radius, or say capital R of y, that's still just 1, right? It's held constant. There's a constant radius from, let's see, yeah, from here to here, that's just always length 1. That doesn't change. Okay, so then this was the volume of the bottom piece. Okay, now I'll leave it to you to evaluate both those integrals and check. You should get for the top piece, you should get pi over 2. That was in the last video. And then you're going to add that to the volume of the bottom piece. The volume of that is just 1. And then you get your answer, pi squared plus 1. Okay, so again, we need to use 2 different integrals here because the radius changes, right? There's this, if you did it from, and you can even check, if you did this integral here, if you did that from 0 to 2, you're gonna get a different answer. And that's because the little radius, that only exists, that function only tells what the little radius is from the top piece from 1 to 2. So that's only that little r of y. This is only valid from 1 to 2. All right, now big R of y, that's valid from 0 to 2. But this little r of y, that's not going to, that you won't have that inside radius show up in the bottom piece. There's only one radius. And remember that the formula is kind of like it's like you take the solid, if it was completely solid, and then you subtract off the missing, or the piece that, the stuff that you take out. We take out what's on the inside. We take out the bowl here. So we're taking, it's like the cylinder minus that space that makes it a bowl. And you don't have that in the bottom, and the bottom is completely solid. So you don't want to use a washer method there. And, the cross sections aren't washers either. Okay, and there's another, you can avoid this 2 integrals by something called the cylindrical shell method. So you could also use that.